Welkom allemaal weer hier voor de laatste sessie hier in de zaal van vandaag. We hebben professor André Dekkers, een oud collega van mij. We waren vroeger bij de radiotherapie collega's. Kijk eens aan. Hij zal zich verder dadelijk zelf introduceren. Wat betreft vragen, wij lopen met een microfoon als je wilt. Dat kan ieder moment in de presentatie en anders aan het einde. Een hele fijne presentatie en dan groot applaus voor André.
Yeah. Thank you. Just checking with you. We're going to do this in English, right? Yes. Yeah. Okay. Because I was confused by the Dutch introduction. Thank you for having me. And I just came in very quickly, so I was here 10 minutes ago. So I haven't seen the other presentation, which is always a bit dangerous if you go like fresh into a conference. Hopefully, I will tell you a story about AI in health and how we view, or at least I view, responsible AI and trust in AI. And I want to convince you that we really talk about opportunities rather than risks in AI, which perhaps for this community is different, but that's how we view it. So I'm a professor of clinical data science at Maastricht University and at the UMC there, and also at Maastricht Clinic. So let's start with the problem in healthcare, at least the problem as we view it. So we have done a very simple test in our physicians, in our doctors, in our oncologists, the cancer treating people. They saw a patient with lung cancer, and then they had to predict, will this patient be alive 2 years from now? That's a harsh prediction, but doctors can make that, and maybe this patient was a bit likely to survive according to the doctor, and this patient less. And so what you can do in such an individual prediction of what we call outcome, survival, for instance, you order your patients according to what you think are the most likely surviving patients. And if you then have the end result of that, after 2 years you know who is alive and who is dead, you can make a quality metric for the accuracy of a prediction. That's often used in data science called error on the curve. If this doctor has perfectly put all the patients that were alive on the right-hand side of the table and all the patients that were deceased at 2 years on the left-hand side, the error on the curve would be 1 because that's how it would look, right? If it is random, like I would probably do it, it looks like this. Right? And this is 0.72. You can see the doctor put some alive patients to the right and some deceased patients to the left, but there are some errors here. So the doctor has not made a complete accurate prediction. What we're trying to do is predict on an individual patient will a patient be alive or not. The problem that we're facing in healthcare that the error on the curve of doctors is 0.5, approximately, which means that a doctor cannot predict outcomes. If you come into my clinic, you have lung cancer, you ask, will I be alive 2 years from now? The answer that you get from your physician is just as good as tossing a coin. And that was done in very experienced doctors, in very inexperienced doctor, didn't matter. It didn't even play a role. And the reason why this is so difficult for doctors is that doctors are human. And humans have a cognitive capacity of 5. That means for any decision, whether you go to this conference, what you will eat tonight, where you go on holiday, or whether or not your patient will be alive 2 years from now, the number of facts that you can take into your head for such a decision or a prediction is 5. If you have to consider more than 5 factors, you're going to make mistakes as a human. The issue with medicine is there are many more facts that you should take into account in any decision or any prediction. And so this explosion of data is a problem. So the topic of the hey ChatGPT, can I trust you, is really in medicine, hey doctor, can I trust you? Right? It's a different question. And the problem is that there are more and more decisions to be made, right? Breast cancer used to be one disease, now it's 8, and all 8 have different therapies where you have to decide on. So that's a problem in medicine. Things are becoming more personalized, which sounds good, but is a problem. And then you might think, well, doctor, you just have to read the literature or the guideline and read the trials. The issue is that if as a doctor you want to read what's being published on lung cancer, you have to read about 9 to 10 hours a day, every day of the year. That's not possible. And the things that are in trials or in literature are very biased, and many things are not trialed. And if you look in medicine, what is the evidence base that we have for any decision we reach? In about half of medicine, we have no idea if the stuff we do works. We have no study that proves that the stuff we do works. Right? And so if you see this mesh, hopefully you can understand why it is so hard for doctors to predict the outcome. But that is a problem, right? Because if we can't predict an outcome for a patient, how do we know which treatment is better for you as an individual? The honest answer is that we don't. We do trial and error. or we follow guidelines. So we want to move to a situation where, we have data, and this is where AI comes in. We want to use that AI information for the next patient, see what happens, and have that data-driven circle running in every hospital rather than doing what we do now. So the potential and the rationale and the opportunity of AI is mostly this. Can we have more predictions of what is best to do in a patient, because that is not a human task. For that, you need a lot of data, right? I'm sure you will realize that. And here's a little calculation that I made a while back. Suppose I want to learn a prediction model in cancer. And so I have, let's say I want to use that decade of data. In that decade in the world, there are about 150 million people in the world that got cancer. Suppose we collect, nowadays we collect perhaps 10 gigs, it used to be less. So the total amount of data is, let's say, 1,000 petabytes on cancer, if we just focus on hospitals. Is that a lot of data? No. It's fine. That's not the size is not really a problem. There is a little bit of a problem that data is unstructured, right? But, just GPT is one of them, obviously, but there are many other tools nowadays that can structure data for us. That's also not a real concern. The real concern in healthcare is that this data is spread around 100,000 pockets. If we want to use hospital data, there are about 100,000 hospitals in the world, and we can't get access to that data. Or if perhaps you want to learn from every single patient on their iPhone or their other system, you have 150 million pockets that you can't get access to. So the question is, how can we learn AIs and validate AIs if we can't get access to that data? Because why can't we get access to the data? The first thing that people ask, if I ask Shanghai, a hospital in Shanghai, give me your data, they would say, well, I like you, Andre, but I don't have time to fill in your Excel sheet and send it over to you. It's, the resources is limiting for me. The second thing people will say is, I don't want you to have my data. Because if if I send you my data, and this is a US problem especially, you might find out that I'm doing something wrong and I get sued. Or they might say, well, I don't want you to have my data because I want to publish my own scientific paper on my own data. Right? So it's a political one. The third problem is ethical. I'm not allowed to. If people say that, what they mean is 1 and 2. Right? In every legal system in the world, it is possible to share data with each other. You might have to anonymize the data. You might have to ask consent of patients to do so, but that's will, that's time. Right? Even in the GDPR, it's very easy to do it right. Technically, it is not difficult. Right? Many hospitals are on the cloud and can give you access to data. But given these barriers, we had to find a way to share data with each other globally, because we need this global 100,000 hospital to work with us. And we have those barriers. So the thing we said is, well, if sharing is such a problem, then don't. Find a way to not share data. But then you have a Mountain and Mohammed problem. Because if not all the data can come to Maastricht has to come to the data. Right? So the mountain doesn't come to Mohammed, Mohammed is going to the mountain. So you'd have to turn it around. But then you have some other challenges. First of all, you have to have a way to send each other questions, like what determines survival in lung cancer patients? Right? That's a question I might have and I want to send to Shanghai. So that question has to be packaged. And nowadays we have container technology, it used to be very difficult, so now we have Docker and things like that. So we have to send another question, that's one. But once Shanghai gets my questions and they double click it and it starts running in the hospital, you would see the risks are involved in that, right? So we need technical governance, we need legal governance to make sure that that train, as we call it, is the question, that train is safe and does what it should do. And the technical legal governance is called track in our metaphor. But then you're still not done. Because if I send a train to Shanghai, that train doesn't understand Chinese. And so China, or this hospital, has to put their data into a state where data can not only be read, you can read a Chinese Excel sheet, but can understand the data. And that's nowadays in medicine or in science specifically called fair data. And so this concept is called the personal health train, and we have made a little animation on that to show you next.
The personal health train's main goal is connecting health data to make them more usable. personal health management requires increasing amounts of personal data. But today, this information cannot easily be used because the data are produced and managed by various healthcare providers, authorities, and more by citizens themselves. These stakeholders collect and manage their data in different ways, making the data hard to find and use. Furthermore, personal medical information is very privacy sensitive. As a consequence, personal health data cannot be used easily by citizens themselves, by physicians, and by researchers. The personal health train goes to the root of this problem by building fair data stations. Fair protocols ensure that data are findable, accessible, interoperable, and reusable. These data stations are connected by tracks which are strictly secured and protected. Fair data trains are constantly monitored, and only trains with the appropriate validation may enter a particular station. To secure privacy, every data station has rules. Each data owner has access to his or her secured station and can easily request and control one's personal information. In addition, the owner can set rules for who can access the data and how it may be used. Communities with common interests, like patient societies, can choose to connect and organize their information through umbrella stations. With this access, a researcher can learn, for example, which cancer patients benefit most from novel therapies such as proton therapy. Or a citizen with a specific variant in his genome can be automatically alerted when new research results, insights, or possible risks become available. In this approach, the information is accessible for research, prevention, and education without the data ever leaving the station. With the personal health train, health data becomes available whilst individuals and institutions maintain control.
So that's the vision of the personal health train, which we, as you see on the top, we made an animation in 2015. We made it for a grant for NWO. NWO thought it was the worst idea ever. We're never going to make it. Luckily, we continued, and this is now won multiple awards, including privacy awards, because you can see, hopefully from your perspective, some of the things that are happening here. First of all, if data doesn't move, it's much less privacy risk. Because it's a question-based system, each individual, each institute gets the question to be asked to their data, and they can decide at that moment whether or not you want to answer that question using your data. Right? So the privacy risk is reduced, but also the control increases about what is being used to your data. And this is vastly different than the old system, which you just put everything on one location. So this is now the de facto way to do research in medicine. This is no longer centralized data, is the old stuff. Just to make sure that you understand how this is done. So researcher, this is a researcher, could be in the Netherlands, has a research question. They would send it to, with packages, they obviously would be encrypted. A Dekker, for instance, encrypted Dekker, they would send it to 3 hospitals. Then in these local hospitals, in this fair data station, there would be a question being asked to the data, like, a simple question like, what's your average age of those patients, to a very complex question about deep learning, for instance. And then the answer to that question is sent back for each hospital to this central location, and then the answers are combined rather than the data. And so this very simple example shows you how this is very easily done, right? Suppose you have 6 centers with these patients. You don't want to share these individual ages for these patients, but you want to have the average age of these patients. So that 34 here, and the average age is 68. What you share with each other is this number, right? How much patients you have and the average age of your institution. And then you can simply calculate, using only this data, what the average age of the patients was. So this is a very simple way of doing it. More complex is it to learn AIs, right? Because it's an iterative fashion. But you can imagine a situation, this was actually a project that we did in Hasselt, where we do try to predict the deceased patients, the black dots in Hasselt, from the alive patients. This was again lung cancer. And if an AI would separate those 2 patients, so you can see this as a predictive AI, it would say, well, Hasselt would say, well, it has to be this blue line because everyone above the blue line is alive and everyone below the blue line is dead. So, but if you send that same train to Liège, it would say, well, no, I have different patients. I think it should be the green line, and Maastricht the purple, Eindhoven and Aachen the other colors. And what you're sharing with each other are these lines and not these individual data points. And by combining the lines, and this is math in iterative fashion, you can actually learn AIs that can predict, in this case, survival in lung cancer patients with much higher AUC. If you remember, doctors are 0.5. These AIs can do that better. And this is now a global thing and more complex, where we now try to learn things like in a CT scan, there's a CT scan of a lung cancer patient. This is a doctor delineating where that scan is. Every image is a different patient. And this is where the AI thinks it is. And these things are learned on a global data set. And the reason to go global is twofold. First of all, globally, you have more data, right? Which means your AIs will be better. But perhaps more importantly, globally, you have more diversity. So by having diverse scanners, diverse people, Chinese, Western Europe, North America, you have much more diversity also in patients and tumors, and your AI would therefore be more applicable worldwide compared to just being learned on Maastricht data, for instance. Okay, so in my field and in the field of AI, and I'm sure it's being discussed, we do see these change in responsible AI, and can we trust AI also has to do not just with the data that we have and the data on which it's learned, and how do we do that in a privacy and secure manner, but also on the type of AI you learn. Right? So the general AI approach for any data scientist is the following. You have a bunch of features, right? You talk to your doctor and say, what predicts 2-year survival in a lung cancer patient? She comes up with a list, right? The age of the patient, the size of the tumor, whether or not it's metastasized or spread in the body, the general condition, the lung function, and they would go on like that. So you have data, and then you split the data into a training and a validation set. You train your model, you validate in the validation set, and that's how you get your answer. It's a very generic approach, right? So it's not at all weird. The only important thing in this is the data, right? Because here are different data sets in medicine from my field of oncology, and this is different AI algorithm. And what you can see, if you have a bad data set, your AI algorithm will not save you. If you have a good data set, any AI algorithm will be okay, right? So the data, and that's why we focus so much on this global data infrastructure, the data is way more determining in AI than the actual algorithm. But it is a classical way of doing it. And for those of you not in AI, this may be for some people that are in AI kind of bread and butter, but the way we're used to do it is just as I explained to you, where we have we ask a physician or a domain expert, what are the features that make this a car, right? And then we put those features in this AI model, in this machine learning model, and then that model will be a formula or something more complex, and that will tell you if this is a car or not, right? So this is analogy in a cat. So if we find ears and eyes and fur and paws and tail in this image, if we find all those things, it's going to be a cat, right? That's the old way of doing it. The issue with this method is that this is, as also all these, right? But it's not a cat, it's a dog, right? So the AI starts making a mistake. And now as a human, you have to think about what makes this a dog. So you have to add features. You have to think again, what is it in the image that is it? Or what is it in the data that makes this a live or a dead patient? This sounds easy enough, but the classical muffin and chihuahua problem shows that it's not. Right? In this situation, it's very hard for a human to say, okay, what makes this a muffin and this chihuahua? I mean, you might say, well, 3 black dots is chihuahua, but this is 3 black dots. And so how do you... And deep learning changes that paradigm, right? So deep learning takes out this person. You no longer need to tell the AI algorithm what makes this a muffin or a chihuahua. You just have to say, this is a muffin, this is chihuahua, this is a muffin, chihuahua, and the deep learning will take out the features that it wants for the image. This sounds great, right? Human out of the loop. And this is, of course, where GPT and systems like that work. Right? We have no idea how GPT works. So we certainly can't trust it, right? Let me give you that answer immediately. But it is learned kind of, and it is performing quite well. Now, the issue with this is this problem, right? these are different approaches. So if you have a human, let's say a radiologist looking at an image of a lung cancer patient, you can ask that radiologist, why do you think this is a lung cancer, right? And that radiologist will tell you that, right? Whether you can trust that's a different story. But they will tell you that, so you can comprehend why is that. If you have a simple rule-based algorithm like a decision tree, you can understand that. The problem with deep learning is that you cannot understand it. Fundamentally, you cannot understand it. And the reason is that this person is out of the loop. So this is bad, but the other things are all good, right? It's very high performance, reproducible, doesn't cost all that time. So you have this conundrum in medicine that the highest performing AI are we don't understand how they work, but the humans that we have, we understand how they work, but they're not very good. And it depends a bit on what we're doing. This is a picture from the AI Act, where they have this classification, and medicine is generally quite high in this tree, right? We also have to do CE marking, lots of validation on AIs, which is not easy. Then we have IP. We have no idea how to detect if a certain hospital was used for a certain AI, so we don't know how to track that. There's new legislation which is called the European Health Data Space. There's GDPR, obviously, and then there's all the security things. And so in this mess, it is actually quite hard to understand as medicine what we should do and in what case we should apply certain things. So that's one of our worries. And let me explain in some application how that boils out and what do we think about risks and use of AI. Let me show you this picture as a base, right? So I've just talked about data. Federated data is important, and how do you securely learn? And deep learning is how do you learn things. And now you have two main application areas. And those two are fundamentally different. The first type of AI, and the AI that I think people think about when they talk about AI, is AI for better processes in healthcare. These are the things that automate away humans. For instance, this automatic delineation of where the lung cancer is, now somebody is doing that by hand, and the AI will do this automatically, right? So now it's faster. You need less people. Is that important to use less people in healthcare? Yes. Because if we go on like this, 1 in 4 people will work in healthcare in 10 years, and that's unsustainable, right? So we need to get rid of people and get rid of doctors in healthcare. So this is an important thing, but the crucial thing to know is you're replacing a human. You're replacing a human, and because you're replacing a human, you have the ability to check the output of the AI. Like GPT, if you ask GPT, write me a summary of this text, as a human, you have the knowledge to check if that summary is correct, right? This is a general thing when you automate humans. But the other AI that we're interested in and that we are more interested in is the AI that can predict this treatment will mean that this patient will live longer than if we would have chosen that treatment. Now you're predicting the future. You're not predicting something a human can check, because human cannot predict outcomes, right? And so these are very different types of AI. These AI, because you can check them, can be a black box. The risks are limited because you can check them, the output. These AIs have to be very transparent. Let me give you some examples. So this is AI that we have. So this is lung cancer being classified into a fat and muscle. That's important information to know if a patient will survive a surgery. Here you see pathology, right? So here's a cut from a tumor, and automatically this is done. This is skin cancer. Take a picture. Is this a skin cancer or not? These AIs are coming in rapidly, and they all are of the type they replace humans. So the AI might say something, and as a human, you can check that. That is important because the risk associated with AI are the risk associated with the data that it saw. This is an example of an AI. You see a picture of a liver, and in the blue, there is the human saying this is where the liver is, or this is the liver, and the AI is in the red. And you can see AI does a pretty good job at finding where the liver is, right? But the problem with this AI is it was only learned by people lying on their back in the CT scan. If you give this an AI from people lying on their belly, it's never seen such data, so it makes mistakes. This is a mistake that a human will never do. And this is where risks in medicine are we have to get thinking about this risk, because a human wouldn't be stupid enough to, the human sees this difference easily, but an AI does not. An AI is not intelligent. If you give this AI a scan of your head, it will find you a liver. So how do we prevent, in medicine, these kinds of scans going through AI? Because this is very different. And so risks in medicine are more in this space. And we are not used to that because this is a breast cancer mammogram, right? A screening where you look for cancer. And this is one patient, this is another patient. And in the bottom, this was cancer, but the AI said it wasn't cancer. But 5 radiologists humans said it was cancer, and the humans were right. So the AI makes a mistake here. And 5 radiologists would say, this is a stupid mistake. Why can't you recognize that cancer? Right? But this is the other situation. 5 humans said, this is not cancer. And the AI said it is. And the AI is right. So AI makes different mistakes. And so the risk analysis that we have are more in these spaces. If you think about ChatGPT, there are also risks associated with the fact that GPT has never seen medical text, because there's medical text in the 100,000 hospitals, and ChatGPT, you can't access that, right? So you might get this, when you ask a question, a medical question, like what's the toxic effect of irradiating the lung for lung cancer, you get these 6 things. And you might say, well, this is fatigue, this is your skin being inflamed. This is your lung pneumonitis, so your lungs are bad. This is your esophagus being irradiated. This is nausea and vomiting, and this is hair loss, right? For a layman, this sounds all great, right? But this isn't true. It never happens. So it is something on the internet that people, and so we can't trust GPT for medical text because it's never seen that. Similarly, when you use GPT to analyze radiology reports, you might, because you want to, for instance, know what type of tumor is that, and this is a type T3, I'll spare you the reasons why. You can ask a very simple rule-based AI, which word did you use to determine that this was a T3, right? A ChatGPT will say, no, it's a T2, right? Somewhere here, of course, ChatGPT produces all this nonsense text from the internet, and here it's T2. And the reason is it interprets the text very wrongly. It assumes things that are not there. It hallucinates, as was just discussed, and so it makes errors. So the thing about better processes, they can be black boxes, but you have to have a human checking it, right? That's the only way to do it. This is a well-known example of ChatGPT. Because you can't ask a deep learning algorithm, why did you do things? So this is the case. I'm not sure if you heard it today already, where a Texas professor uploaded the thesis of his students to ChatGPT and asked the question, did you write this? Right? Because he was suspecting their students to write the whole report using ChatGPT, and he said it wasn't possible. So this professor uploaded it to ChatGPT, and ChatGPT said, yes, I wrote that. But he was wrong. ChatGPT actually claimed that it wrote the email the professor sent to the students to flunk them. Right? So the problem with black box AIs like GPT, but any deep learning AIs, is that we can't find why it's doing that, and that is a problem. It always gets wrong in the situation which it hasn't seen. So this is the Greek playing around with a self-driving car. A self-driving car knows it can enter, do the dotted line, but it can't enter or it can't pass a solid line, so it will stay there forever. It doesn't know what to do. Right? These are issues with AI algorithms in medicine. So the risks are more about how can we make sure that it only sees the data in which it was trained, because we can't check how it's working. The other issue in medicine is that we don't trust AI. And we have a very different way of looking at AIs than we look at humans. If you see this Guardian thing, driver dies in fatal crash, you might say, why is that a problem? That person might have been, why is that in the news? It's a problem. Why is it in the news? Maybe they have apped or were drunk or didn't do anything. But once it is a Tesla that does this, we say, oh, right? And so we have this asymmetric expectation that we think an AI in medicine should be totally right, where a human is fallible. And so that is something in the risk discussion that we find hard. So we demand much higher things about AI than we use about humans. But generally, we do accept in AI this AI for better processor because the humans are replaced by them, and we can check if they are, if the result of that AI is good or not. But now look at the other ones, the better outcomes. Suddenly you see the AIs becoming very simple. Here what you see is just 6 factors, and this is a very simple model, a logistic regression model. What we're predicting here is how long will this patient live. And that's important information for a lung cancer patient in this case, because we want to have the discussion whether or not you still want to be treated or not. And so if a patient only lives a couple of months, like in this case, you might want to consider not giving certain treatments to that patient because they might spend more time at home with their loved ones, right? So here, we're predicting the future, and we don't know if this is correct or not. So there we have to have much more transparent AIs. Such AIs are very different in the world, and this is an AI from India, where we're predicting if a patient has diabetes or not, or another state called pre-diabetes, so almost diabetes. And so again, this is very simple AIs where you have some simple features, but they have to be learned locally, because if you use a Western model in India, it doesn't work. So these AIs need to be localized, so people are different in the world. A specific case about India is that they have a lot of people that are vegetarian. About half the population is vegetarian, so they can't learn. We can't learn in Maastricht that vegetarianism is important for this because we have so few vegetarians. Okay? This becomes already some more risky stuff, right? Because now what we're trying to do here is we're trying to predict in a heart failure patient whether or not a medication that they take should be increased or decreased. In these patients with heart failure, they take diuretics, so that makes them pee to lower their fluid balance. But if you take too much of them, your kidneys will fail. So you're kind of balanced in between that. So here the risks are that we might give a wrong, the AI might give a wrong recommendation, and the patient might, in the worst case, die of that. So there's lots of discussion about whether such AIs are going to be acceptable or not, but they are still quite simple for that reason, because we have to understand. The most extreme case we now have in medicine is where AI simply decides autonomously. This is the newest thing. This is proton therapy. It's in my field, so it's a new therapy. If suppose you have a brain cancer, this thing here, and traditionally we would irradiate those patients with this yellow beam, and that means that not only the tumor gets radiation, but your whole brain gets irradiation, especially this part. Right? The new therapy is called proton therapy. The beam stops here, and so this whole part of the brain doesn't get irradiation. You might say, well, this is always going to be better than that. True, but only if there's an important part of your brain there. If it's not that important, it doesn't really matter. And then not all your parts of the brain are important. Right? So, and we have this situation where, you might think your whole brain is for now, it's not true. So we have, because we are resource limited in medicine, right? So we have 3 proton therapy centers in the Netherlands, 1 in the north, in Groningen, 1 in Maastricht, and 1 in Delft, which means every year we can treat only 1,600 patients. But there are 50,000 patients in the Netherlands that get irradiated. The treatment is 5 times as expensive. This is more expensive than that, right? We don't have any evidence. We don't know in which it works. So the question is, who gets it? This is the first time we sat together and we said, we're not going to let doctors decide, because doctors cannot predict what is better or not. So here the AI decides. The AI will take this treatment, simulate that treatment, simulate that treatment. It will calculate the toxicity difference, right? So the brain toxicity in this case. And the computer says no, and the computer says yes. Right? So, and if the computer says no, by law, we are not allowed to treat you. This principle may sound exotic, but it is happening already, right? Already 3 years we're doing it like this. And this has gained much interest from the health insurance companies, obviously, because why don't we do this for expensive medication, right? Why don't we do it for many more decisions in medicine? So this is coming. Final few slides to get you thinking and to have also a bit of fun. Data quality is often being mentioned. Garbage in, garbage out, that stuff. And here are some problems that you have in medicine, like data might be missing, might be incorrect, or things that are at least implausible. But let me give you this picture. Who is this? This very famous person. You all know that. Who? You, right, it's me. 20 years ago, it's me. And so Gilbert knows me like that, I guess, right, to just introduce me. But so this was me at my PhD 20 years ago. and this is a picture taken, I'm in a lounge of an airport taking a picture of my hospital card. So you might say this is quite bad quality data, huh? Right? Because probably many of you didn't recognize me. But AI says that this is the same person, easy. So what we think as humans as high quality data is not the same as an AI thinks as high quality data. And that is a problem because we think we know what's good, but we don't. And in the new, so garbage in, garbage out is simply not true because we don't know what's garbage for an AI algorithm. And GPT is an example of things that are learned on very bad data, the internet, and is extremely powerful at what it does, right? So foundation models are coming. Obviously, GPT is on text, but all these are coming as well, also in medicine, and these will be very powerful. We don't understand them, so we have to take care that they're used in the proper way. But it's certainly not true that garbage in is garbage out. And so this has really changed our thinking about what should we record about patients, what should we include, and where should we learn from. So I said this is the same person, right? And I think you can agree that I've barely aged, right? But we now have an algorithm that can look at your face and can guess how old you are. It's called the face age algorithm. So the face age algorithm is learned on public data of 60,000 people. And so for image you can see, and it can determine how old you look, right? The age of your face. Now, when we try this in our cancer patients, these are cancer patients, we first of all found that cancer patients look about 5 years older than they are. That's an interesting observation. But what's more important, the difference between how old you are chronologically in your passport and how old you look is quite an important determinant of how long you will live. For cancer patients, this is again quite important information because you want to know how long you will live because you want to plan your life, right? So for us in medicine, this is not controversial. But in real life, this is a problem, right? Because now we develop an AI algorithm that on your LinkedIn page can say, it's not going to be that long for you. So think about the implications of that for life insurance and getting a job. So different types of risk, I would say, huh? So to the final slide. So why is AI for us more opportunities than risk? Because we're facing this real issue that we need AIs in medicine to predict what will happen to patients and what treatment is best. We also need AI to make medicine more efficient because we can't go on the way we are with the aging population, with the limited workforce, if we want to spend our money on other nice stuff of society, right? The trends in medicine are federated data, right? And fair data, because you can't determine risk if you don't know what data means. So fair data is important, right? We have to understand what the data means, even in Shanghai or in Maastricht. But federation is a fact, right? We're not going to send data around. It's impossible to send data from China to Europe or from Europe to China, for that matter. It's going to be never going to work. But we need each other's data to do this. Deep learning is obviously a big trend. But what's more important is that we see now slowly companion AIs coming that will decide you will get this therapy or not. Lots of cautions, right? Bias, obviously I haven't talked about that, but some of that. The ethics that I just showed you of a face-stitch algorithms is stuff that we don't know. So what is responsible, what is compliant? It is irresponsible not to share data. Many more people in medicine have died from not sharing data than from sharing data. Right? And so the idea that risk is the risk approach is the right one goes against everything in medicine, and we will not do it. We have to develop AIs to make it better, right? And compliance in terms of privacy, we understand. I think it's clear, but the other LC is not. What does it mean for autonomy? What does it mean for the patient-doctor relationship? If I have cancer and I really don't want to be treated, but my family has an AI that says I should get this very expensive toxic drug, but I really don't want it, will I lose my autonomy? Will I get pressure to choose that treatment that I don't want? It's those questions that we're worried about much more than the risks. Thank you for listening, and I'll have some time to take questions, hopefully. Now I can see you finally.
LC.
Oh, sorry. LC is ethical, legal, and societal implications. A good one. That's your jargon that we use. So the the problems that we have outside of the actual use, LC. Yeah.
Other question? Yeah.
Yeah, I'll repeat. Yeah. Right. Yeah, it's a good question. So the question is, if you do federation, maybe if I paraphrase it, you send a question, but you don't see the data, right? So how can you be sure that the data is perhaps valid, accurate, makes sense, right? Is relevant. So we have all, before we start the learning from data, we do have lots of quality things that go around, right? Like saying how much missing data do you have? What is the difference between the patients, right? To give an example of the things that we encounter is in Shanghai, that's, we really do work with them, so that's why I use them often, is in Shanghai, they don't have a central death registry like we have here in the Netherlands, right? So that means, how does a Chinese hospital knows if somebody is alive or dead, right? If the patient comes for follow-up after their treatment, they know the patient is alive. If the patient dies in their hospital, they know the patient is dead. If the patient doesn't show up for follow-up, they don't know. That's missing data. But it's extremely biased missing data because in cancer, especially lung cancer, most of the patients will be dead. Right? So you have this situation where China has a tremendously biased set. If you look at survival rates from cancer in China, they're 80-90%, right? Well, we have maybe 25% in the Netherlands of lung cancer, right? So that's, yeah. So then we do tests. Should we include Shanghai or not? Does that make the AI better or not? The honest answer is it always makes it better. Even if the data is of very low quality in our human eyes, including even bad quality data is typically much better than excluding it. So we're not too worried about data. We do detect data quality differences, but then we can try to include them or not. So it's not a big worry. Yeah. Yeah. Sure. Sure. Yeah, no, it's a good question. So can you increase the quality of the learning, right? The quality of the AI, perhaps by you can do things like imputation, right? Filling in the missing data. You can, of course, increase the data set by just including more hospitals. And you can actually use sometimes a situation that excluding a certain very bad quality hospital increases the quality of the model or the AI for everyone else, right? So we do play around with that, right, to see if we can be better. Yeah, good question.
I've heard something that in some cases in medical research, you're also able to create additional populations to make your prediction or your outcomes of your research better.
Sure.
Is AI also used for that?
Yeah, good question as well. So we're always data hungry, right? So we always have limited data, and you can use all kinds of generative AIs, right, to create data, and these work quite well. So we use generative AI to create what we call synthetic data, right? I'm sure you know it, right? Which is data which looks like the same patients, but is not. So that's data which is anonymous and you can share more easily. But we also use generative AI to create, for instance, fake pictures for lung cancer patients if we have too few. So that when you do this, increasing the data set by generative AI or by bootstrapping even, right? You do see an improvement in the AI generally. Yes, we do that a lot. Because we always have too few data. I mean, it sounds great, right? 150 million patients. But if you think about how many lung cancer patients are in there, maybe 10. How many patients do we, have a certain subtype? It's going to be less. And so we're always hungry for data. Yeah.
If I can ask a question about the system you have with executing the computations in another hospital.
Mm-hmm.
So did you develop the system or standard, or what is its program for executing these computations in a standardized manner? Or?
So we use mostly containerization technology like Docker or Podman nowadays, but Docker is probably the easiest one. So we send each other Docker with the application, and then especially for deep learning, you need GPUs and environments like that, but these hospitals generally have that. So the interoperability between computer systems used to be very hard, but now it's really easy with containerization especially. What is much harder is the interoperability in the data. it still takes a lot of work to, to have to what the Chinese call male and female and we call man vrouw to make that, the same code so that the algorithm understands that that's actually the same thing, a male and a man. So I think that's way more problematic than the execution environment, if you want. Yeah.
Right. So they still have to make sure the data is in the right format.
Yeah. So, and that's probably where we have still the most to do, right? How can we quickly convert a Chinese electronic hospital record into a fair data station in which data is coded exactly the same way, is structured exactly the same way, so that an AI can come in and learn? Right, that is still one of the major problems. Although, again, large language models are kind of interesting for that because they might be able to structure the data much quicker than a human can structure the data. But that's our main barrier still.
Okay, thank you.
Yeah. Good question.
Zal van je deze kant brengen. Hij komt dan.
You just said that there's always data hunger. So the more data, the better. Even if the more data, the additional data is bad data. You just mentioned the Chinese example.
Yeah.
Why is that the case?
Mostly because AI algorithms, especially deep learning ones, but also more classical online Bayesian networks, can actually learn from the data that is there. And because you have such huge data globally, the fact that there are sometimes very bad data points in there are being averaged out by all the others that have good data. So typically, because you have a mix of data, you can establish certain relationship, let's say between age and survival, right? That's you can learn that relationship. And even if a data set doesn't have all the other factors, but just the fact that how old is somebody and somebody is alive or not, that fact that you have the rest can be missing, that already gives some information to the algorithm, right? So an algorithm typically nowadays learns piecewise. And so even if you have these piecewise data, you can learn better AIs than if you remove that piecewise data. That's in short what happens. But of course, it only happens if there is also some high quality data in the network, right? Only bad data becomes very hard. You need to let's say average out the contradictions, the noise, things like that. But in general, it's our feeling. The thing about data hunger is also time. The medicine changes, right? Every day new medicines come into the floor. So you have this issue, for instance, in predictive modeling that you are learning in lung cancer patient survival, but now there's a new drug which changes survival tremendously. So but you only have information of the last few months on that. So you have very few patients. And so there are techniques then to put more emphasis on these last patients to very quickly learn a new algorithm that understand there's a new medication that now needs new predictions. So this data hunger is a continuous battle because things are not static. And so even in those situations, if you have some information on only a few patients on this new drug, and you can again with bootstrapping or generative AI put more focus, put more of these patients into the mix, it will very quickly adapt to the new situation and be useful again. So that's the kind of the game we're playing, if you understand. Yeah. Thank you.
It's working, yeah. That it's time to close this session. A big thanks for André. Applaus.
Graag gedaan.
There's some talk